And what we're going to look at now in this part of the quadratic function is to look at the roots of the quadratic function. And when we talk about the roots of the quadratic function, we are referring to the places where the graph cuts the x-axis. So the x-intercept of the places where the graph cuts the x-axis will give us the roots of the quadratic function. Is it possible for us to algebraically find these roots? Yes, definitely we can. Because if we were to just reference it back to the graph, it is the place where the graph of y is equal to fx intersect the line y is equal to 0. Because the line y is equal to 0 represents the x-axis. So in order for us to find the roots of the quadratic function, we are going to, of course, look at a function where it is expressed in terms of this, a quadratic expression. A general quadratic expression, ax squared plus bx plus c, where a is not equal to 0, like what we have discussed. If a is equal to 0, then the entire thing is going to be just bx plus c, so it is going to be a linear expression instead of a quadratic. So the place where this graph is going to cut the x-axis, the line y is equal to 0, will be the place where we are going to be letting fx be equal to 0. So let's do that. So by letting fx be equal to 0, we are going to try to solve for x, and this x will give us the roots of the quadratic function, which means that we are going to be looking at ax squared plus bx plus c is equal to 0. Let's try to find a way to solve this algebraically. Because a, b, c, they are still unknown to us, so we are really trying to solve for a general quadratic equation. Is there any processes that we have learned before that can help us to do this? Yes, there is. We can make use of completing the square. But in order for us to complete the square for this equation, we need to make sure that the coefficient of x squared is positive 1. So since a is not equal to 0, we are going to divide this throughout by a, which will then give us a x squared plus b over ax plus c over a is equal to 0. Let's complete the square for the expression that is on the left-hand side, and that will be x plus b over a divided by 2, so b over 2a square minus b over 2a square plus c over a. This is equal to 0. Let's try to make x the subject. So we have x plus b over 2a square. This is going to be equal to this. I'm going to bring it over to the right-hand side. And if I were to square this term here, it's going to be b squared over 4a squared. Then minus away c over a. And I'm going to square root both sides. But before that, I'm going to try to make this into one single expression first. They share a common denominator of 4a squared. So this is going to be b squared minus, from the top and the bottom, I'm going to multiply this by 4a over 4a, which will then give me the common denominator of 4a squared, which means that here is going to be 4ac divided by 4a squared. So this is equal to this. If I were to square root this, that means x plus b over 2a. This is going to be equal to plus or minus square root of b squared minus 4ac divided by 4a squared, which is equal to plus or minus square root of b squared minus 4ac divided by square root of 4a squared, which will give us a 2a, which means that x now is going to be equal to, bring this over to the other side, we will have a minus b over 2a plus or minus square root of b squared minus 4ac divided by 2a. They share the same denominator. So x is going to be equal to minus b plus or minus square root of b squared minus 4ac over 2a. And this gives us the quadratic formula that probably you guys are already pretty familiar with it. What I would suggest that you try to do to challenge yourself, not exactly to challenge yourself, but to just learn this formula even better, is to go through this process of deriving this formula. In fact, it is just a process of us trying to solve for a quadratic equation. But when we start to look at this, we are more interested in finding the roots of the quadratic function. We are trying to find the roots of this particular equation here, which was what we were discussing just now. But what if we are not that interested in the roots, but we are more interested in just the type of roots? What do I mean by type of roots? Because if you were to just think about it, it is actually possible for a parabola to be cutting the x-axis in three different ways. It can be cutting the x-axis in this way, then we are going to be getting two roots. It is also possible for a parabola to be cutting the x-axis in this way, then we are going to be getting just one root, or it can also not be cutting the x-axis at all. So these are the three possible types of roots that we will be expecting out of a general quadratic equation. So is it possible for us to just discuss the type of roots, to just discuss the nature of roots, okay, which is my next focus? Is it possible for us to look at the nature of roots without having to go into the actual roots itself? Yes, it is possible, and the hint or the inspiration comes from the result of what we have just proven, which is the quadratic formula. The quadratic formula, which is meant to find the actual roots of a quadratic equation, but within this formula, there lies this square root. And within this square root, there is this b squared minus 4ac. And I'm going to make use of this b squared minus 4ac to discuss with you guys about the nature of roots of a quadratic equation. The nature of roots, okay? Please take note, I'm not interested that much in the actual roots itself. I'm interested in the type of roots, the nature of roots. So it will be either of these three cases. So let's take a look at this b squared minus 4ac, and we will explore together how is it that just by looking at this b squared minus 4ac, we will be able to look into the nature of roots. So let me erase this. And from what we have discussed, we know that if this were to be equal to 0, then x is going to be equal to minus b plus or minus square root of b squared minus 4ac over 2a. So we are going to focus on b squared minus 4ac. And this b squared minus 4ac is very commonly termed as the discriminant of this quadratic equation. So if I were to look at the discriminant, b squared minus 4ac, how is it possible for us to determine the nature of roots, the type of roots that we will be expecting? If you think about it, what if b squared minus 4ac is a number that is bigger than 0? There's only three possible outcomes for b squared minus 4ac, right? It can be either bigger than 0, equal to 0, or less than 0. So what if b squared minus 4ac is bigger than 0? Let me write it down here. So b squared minus 4ac, if it is bigger than 0, how many roots do you think you will be expecting? Looking at this, we will be expecting two roots, right? Because one of the roots will be x1. Let me call this the first root, okay? One of the roots will be minus b minus square root of b squared minus 4ac over 2a. Or the other root is going to be equal to minus b plus square root of b squared minus 4ac over 2a. So we are going to be expecting two roots, and these two roots are different from each other because numerically minus square root of this and plus square root of this, I'm going to be deriving two different numbers. So this will be called two real and distinct roots. That means the moment when we check the discriminant of a quadratic equation and we realize that this discriminant is bigger than 0, without having to actually find the roots, we can already determine that this equation has two real and distinct roots. In case this is confusing, let me just jump a little bit, okay? I'm going to come back to this. What if b squared minus 4ac is equal to 0? Okay, just in case you have a bit of confusion about, what do I mean by having two roots? Isn't it like always going to be having two roots? Not necessary. Because what if b squared minus 4ac is equal to 0? If it is equal to 0, that means x1 is going to be minus b minus square root of 0 over 2a. And the other one is going to be minus b plus square root of 0 over 2a. And can you see that these two are actually exactly the same? Minus b over 2a. This is also minus b over 2a. So when b squared minus 4ac is equal to 0, we're expecting, yes, x1 and x2 has two roots, but these are going to be two equal roots. So I'm writing them down here. We have these two scenarios. When b squared minus 4ac is bigger than 0, we have real and distinct roots, two different roots. When b squared minus 4ac is equal to 0, then we have real and equal roots. Real and equal roots. Okay, we can see it as just one root. I mean, some people do that. Or we can just see them as two roots, but they are equal. So for these two cases, like what we were discussing just now, we can actually have a visualization of how the graph is going to look like. We don't know how exactly it is, because to know the exact way that the graph is going to be intersecting the x-axis, we need to find the roots itself. But now we are discussing about the nature of roots. So it gives us an overview. It gives us a quick idea of how the quadratic graph is going to look like. Because if this were to happen, if b squared minus 4ac is bigger than 0, that means this quadratic expression is going to be cutting the line y is equal to 0 at 2 points. It is going to have two roots, which means that if a is bigger than 0, then we will be expecting a graph that is like this, when a is bigger than 0, and it is a parabola. And this graph is going to be cutting the x-axis at 2 points. So it will be x1 and x2. Of course, a can be less than 0 also. If a is less than 0, then we will be expecting the graph to be a set phase parabola, and it is going to be cutting the x-axis at 2 points, x1 and x2. And if it is a case that is like this, when b squared minus 4ac is equal to 0, we will be expecting just one intersection. Two roots, but one intersection. In fact, the two roots are going to merge into each other. So if b squared minus 4ac is equal to 0, how will we be expecting the graph to be like? If a is bigger than 0, if the coefficient of x squared is bigger than 0, we will be expecting a smiley face. And since this is going to be cutting the x-axis at just 1 point in order for us to be getting just one root, that means it is going to be cutting the x-axis in this way, where we will be expecting one single root. And this is both x1 and x2. Similarly, if a is less than 0, we will be expecting a set phase, and this will be cutting the x-axis at just 1 point, and this point is either x1 or x2 since they are exactly the same. And do you feel that it is a little bit strange that we call this real and distinct roots, real and equal roots? Why don't we just call this, term this as distinct roots? Why don't we just term this as equal roots? The word real indicates to me that they are non-real numbers. Okay, non-real numbers, we will be learning this in the A level. So non-real numbers, which are called complex numbers. Okay, maybe some of you have already gotten a little bit of idea about complex numbers, but for real numbers, it is going to be when we can do a square root to a positive number, right? When we square root a positive number, we're going to be getting a real number. If we were to square root a negative number, we're not going to get any real solution. If you were to press this in the calculator, square root of -2, the solution is just going to be looking weird on our scientific calculator. So this indicates to me that I'm not getting any real roots. That is why just by looking at b squared minus 4ac, and if b squared minus 4ac is less than 0, then we will not be expecting any real roots. They're actually complex roots, okay, but that will be in the A level. So in O level, we will talk about it as if there are no real roots. Because when b squared minus 4ac is less than 0, we will be doing a square root to a negative number. It will not produce for me a real solution. So for this case here, we do have an example. Let's take a look at this example. So if we are looking at this quadratic equation, 4x squared minus x plus 5 is equal to 0. You can try to press this into the calculator. The calculator will give you no real solution to this particular equation. But we can also do a quick check. Let's say we are not interested in the actual solution. We're just interested to find out the nature of roots of this particular quadratic equation. So what we can do is we check on the discriminant. And the discriminant is b squared minus 4ac. So let's take a look at the discriminant of this. The discriminant is going to be equal to b squared, and b is -1. So b squared minus 4a is 4, c is 5. So this is going to be equal to -79. It has no real roots. Okay, do give it a check. Take out your calculator, try to press this into the calculator to just verify for me, okay, whether this equation is really going to have no real roots. But we can already do that by looking at this discriminant. Let me show you some examples of how this idea of discriminant can work. So Oh, let's not forget about the graph, okay? So for the graph of the case where b squared minus 4ac is less than 0, then we will not be expecting the graph of y is equal to fx to be cutting the x-axis. So if it is not cutting the x-axis, when a is bigger than 0, the coefficient of x squared is bigger than 0, we have a parabola that is a smiley face. And since it's not going to be cutting the x-axis, the graph is going to look like this. It's going to be hovering above the x-axis. If a is less than 0, then we will be expecting a sad face. And for this sad face, since what we have discussed is that b squared minus 4ac is less than 0, there's not going to be any real roots. That means the graph is not going to be cutting the line y is equal to 0, which is representing the x-axis. So we have a scenario that is like this. We're going to be talking about these two scenarios a little bit more in the next part. But in general, this is called an always positive scenario. For fx, this is called a always negative scenario. Okay, but we are going to talk about this a little bit more. But before that, let's take a look at two examples. First, let's take a look at this. So we are now given a quadratic equation. This equation is 2x squared plus kx. This is equal to minus 18 minus x. And we are told that in part 1, this quadratic equation has real and distinct roots. We are supposed to find the range of values of k. K is here. It has real and distinct roots. The first thing that I want to do is to try to see this from the perspective of a quadratic function, a quadratic equation. So let's move everything over to the left-hand side, which will be 2x squared plus kx plus x plus 18. This is equal to 0. And I'm going to regroup this so I can see this more of the kind of quadratic equation or the quadratic expression that we are more familiar with. So x squared, I'm going to leave it. X, I'm going to group it together, and the coefficient is going to be equal to k plus 1. X plus 18, this is equal to 0. And please take note, this question is not trying to ask us for the roots. This question is actually telling us that there are going to be two real and distinct roots. And our focus is actually on k. K is part of the coefficient. Okay, so this question is not focusing on the roots itself, but it is just making use of the nature of roots to give us hint in order for us to find k. So in part 1, since we are told that for this particular equation, it is going to have real and distinct roots. For real and distinct roots, b squared minus 4ac must be bigger than 0. Like what we have discussed just now. For real and distinct roots, b squared minus 4ac must be bigger than 0. So for part 1, we are going to let the discriminant, I'm going to just use d, okay, to represent discriminant. So the discriminant must be strictly bigger than 0, according to what we have discussed in a short while ago. So discriminant b squared is going to be k plus 1 squared minus 4a, a is 2, c is 18. So this is supposed to be bigger than 0. I'm going to try to make use of this inequality here to solve for k. And this inequality, in order for us to solve for it, we need our knowledge for quadratic inequalities. So do check out the chapter on quadratic inequalities if you have not done so. Then we are going to make use of what we have learned in that chapter to solve this particular quadratic inequality. I'm going to re-express the left-hand side. The left-hand side looks like a quadratic expression in terms of k. So this is k squared plus 2k plus 1. Minus away this is 144. This is bigger than 0. So we have a k squared plus 2k minus 143. This is bigger than 0. I can factorize this. Factorizing this gives me a k plus 13. And a k minus 11. This is bigger than 0. And according to what we have discussed in the quadratic inequalities chapter, we are going to try to sketch a graph that represents the left-hand side. So my graph will be with respect to the k-axis. And since the coefficient of k squared is positive, so we are going to be expecting a parabola, that is a smiley face. And this will be the roots, which I can get from here. This here is going to be equal to minus 13. This here is going to be 11. So what is the range of values of k such that this expression is going to be bigger than 0? So the place where this expression is bigger than 0 is indicated by the vertical axis, which is going to be, let's say y is equal to this. So it is going to be the y coordinates of this. It is going to be here and it's going to be here, which means that as long as k is less than minus 13, or when k is bigger than 11, the y coordinates, which represent this, will be bigger than 0. That gives me my answer. K is supposed to be less than minus 13, or k is going to be bigger than 11. This is for part 1, where we are going to be experiencing real and distinct roots. Let us take a look at, let us have a check of our interpretation, because I think part 2 is a little bit more interesting because it just mentioned that it has real roots. Okay, this equation here has real roots. If you were to look at what we have, real and distinct, real and equal, there's no real roots, but this question says that we are going to be experiencing real roots. So what does it mean? If this question were to say that this has real roots, that means this will have either two distinct roots, or it has one root or two equal roots. Which means that in part 2, it is talking about two possible scenarios that can happen. The first scenario will be when b squared minus 4ac is bigger than 0. The second scenario will be when b squared minus 4ac is equal to 0. These two cases will give me real roots. It is just that one of them is real and distinct, the other one is real and equal. That is why for part 2 of this question number 1, we are going to let the discriminant be bigger or equal to 0. Bigger than 0, two distinct roots. Equal to 0, two equal roots. And both are talking about real roots scenario. So it is going to be the same thing. Let me just go through the process, okay? So it is going to be having this b squared minus 4ac to be bigger or equal to 0. And if I were to work through this, I'm going to be getting a k plus 13 multiplied by k minus 11. This is bigger or equal to 0. And sketching the graph that represents this, it is going to be a smiley face. Here it's going to be equal to minus 13. Here it's going to be equal to 11. And if this is y, and I'm drawing the graph of y is equal to kx, k plus 13 multiplied by k minus 11. So what is the range of values of k such that y is bigger or equal to 0? Is going to be this portion and this portion inclusive of minus 13 and 11. So for this case, k is going to be less than or equal to minus 13, or k is going to be bigger or equal to 11. There's another question that I really want you guys to take a look at, because this is an interesting question. In this question, question number 2, okay, let me just erase the board first, okay, then let's explore and look at question number 2 together. The reason why question number 2 is more interesting is because we will not be able to instantly see the application of the discriminants concept. It's going to come later. That is why for this question, we need to have a slight change in the perspective, okay? But it is a very, very interesting question. It is especially useful for A-level, okay? But in O-level, it is still going to be very useful. It is a typical enough questions for us to really want to make sure that we get it, okay? Especially the idea that is behind it. So we are supposed to find the values of k such that these two graphs, first one is a line. This line is given to me as x plus 3y is equal to k. The other one is a curve, so y squared, this is equal to 2x plus 3. We are told that these two graphs, they are not going to be intersecting. And we are supposed to find the values of k such that this is going to happen. K is here. So how are we going to do that? Okay, like what I was saying, we are not going to be able to apply discriminant instantly. So it is probably going to come later. So how are we going to start to process this question such that by the time when we finish it, we will be able to find the values of k? What I propose that we do is to try to make use of the idea of simultaneous equation. Okay, this may feel a little bit weird because according to what this question says, this and this, okay, I mean, let's say this is, let's say this looks like this. Let's say it looks like this, and we have a line, the line, let's say it looks like this. So this is like 3, this is like x plus 3y is equal to k. This is like y squared is equal to 2x plus 3. So the question says that these two graphs, they do not intersect. So when two graphs don't intersect, we usually don't talk about simultaneous equation, right? So why do we still want to do simultaneous equation? Okay, let's be a little bit patient. Let me show you why simultaneous equation actually will work for this particular question here, okay? So I'm going to still try to solve this as a pair of simultaneous equation. So for this equation, I'm going to try to re-express it. I'm going to try to re-express this equation to make y the subject. So y is going to be equal to k minus x divided by 3. I'm going to call this equation number 1. And this, let me just call this equation number 2. I'm going to solve this as a pair of simultaneous equation. So I'm going to substitute equation number 1 into equation number 2, which will then give me a k minus x over 3 square. This is equal to 2x plus 3. This in the numerator, we have a k minus x square. Then this is going to be divided by 9. This is equal to 2x plus 3. I can multiply 9 across to the other side, which will give me an 18x plus 27. And as for the numerator here, let's expand it. So we have a k squared minus 2kx plus x squared. And I'm going to bring everything over to the left-hand side. So if I were to bring everything over to the left-hand side, we have a k squared minus 2kx plus x squared minus 18x minus 27 is equal to 0. You know what I'm trying to achieve? Because from the expression that I can see now, I know this is a quadratic expression. Okay, this is a quadratic expression. So this question, in a way, it led me to a quadratic equation, which I know we have learned some in this chapter, definitely. A few different ways that we can now process a quadratic function or a quadratic equation. So I'm going to try to regroup this so that I can see this more as a quadratic equation. So x squared is going to be here. I'm going to group the x together, which is going to be minus 2 of k plus 9x. Okay, so this will become the coefficient of x. Then the term that is independent of x will be k squared minus 27. This is equal to 0. And this is where the idea of discriminant will be applied. You think about it together with me, what we are trying to do is to solve this as a pair of simultaneous equation, which means that we are expecting an intersection, which means when I try to solve this as a pair of simultaneous equation, we are expecting solutions. We're expecting roots to this equation. Let me repeat again. When we are trying to solve this as a pair of simultaneous equation, we're expecting roots to the equation that I found. Okay, I'm expecting roots. But according to what this question says, there's not going to be roots. Why? Because the question says that these two graphs do not intersect. So we are not expecting a root, which means that whatever that we've derived here shouldn't give us any solution. It shouldn't give us any real solution. And this happened to be a quadratic equation. So that means my conclusion is that this quadratic equation has no real solution. It has no real roots. Does this resonate in your head? What are we going to be making use of? We are going to be making use of the idea of discriminant, since the idea of discriminant is going to be applied for a quadratic equation. And if there were to be no real roots to a quadratic equation, that means b squared minus 4ac, that means the discriminant is supposed to be less than 0. So from here, we are going to let its discriminant be less than 0. And its discriminant is going to be b, which is minus 2, k plus 9. So b squared minus 4a, a is 1, the coefficient of x squared. So 1 and c is the term that is independent of x. So it's going to be k squared minus 27. And we are letting discriminant be less than 0 because this quadratic equation here is not supposed to have any real roots since the two graphs are not intersecting each other. So let's try to solve this quadratic inequality. Here we have 4 k plus 9 squared minus 4 k squared minus 27. This is less than 0. 4. I'm going to divide this throughout by 4, which will leave me with just a k plus 9 square. Expanding k plus 9 square, we have a k square plus 18k plus 81. Then minus away 4 will also disappear because we have already divided this throughout by 4. And since we are dividing it by positive 4, the inequality sign remains the same. And here we have a k squared minus 27. This is less than 0. K squared, this will disappear. I'm going to be left with a 18k plus 108 is less than 0. So 18k is going to be less than minus 108. And our answer now is k is supposed to be less than minus 108 divided by 18 minus 6. So these are the few examples. These are some of the examples that we can see how discriminant can be applied. It is mainly to be applied to a quadratic equation, where we are when we are more interested in the nature of roots instead of the roots itself. And what I want to do in the next part is to explore with you guys this idea of having a quadratic function to be always positive, or it can be always negative. So let's take a look at the next part of the